All right, we'll move to the next talk, which is Kathleen Mandt, mapping lunar permanently shadowed regions in the far ultraviolet.
Okay, thank you, everyone. My name is Kathy Mandt. I didn't introduce myself earlier when I was chairing the morning part of this, or the earlier part of this. I'm the volatiles coordinator or theme lead for the Lunar Reconnaissance Orbiter, and I'm also the project scientist for the Lyman Alpha Mapping Project. And I'm going to be talking today about the work that we're doing with LAMP to map the surface of the moon in the far ultraviolet. So LAMP is a far ultraviolet spectrograph, and we take observations during the day and during the night. We operate in the day with this door, oops, I was laughing at the other people who were doing that, and I do it myself. So during the day, we operate with this door here closed, and all the light that can get in is through this pinhole in the middle. And we do that to avoid saturating the detector. During the night, we open this door, and then we can allow a lot more photons in, and we can take observations using starlight of the permanently shaded regions. And this is how we're able to map regions where sunlight, direct sunlight never shines. So we have two operating modes, day and night. And then recently, as the beginning of the extended mission 3, we opened up this fail-safe door here, which was a permanent operation. So that opened up, and now we have this gap that we're able to increase the flux of photons during the day so that we can get better observations of diurnal hydration, the work that Amanda Hendricks has been doing. So those are our operational modes. We've already had several results that have been discussed today. The overview included some of this. The main focus of this is to look for surface water in the permanently shaded regions. And what's important to understand about LAMP is that we are an integrating instrument. We have to take several orbits over several years of observations and count individual photons at a time. We can even name them practically, in order to get enough signal to make maps in the ultraviolet of the surface of the moon. Now, the first publication that we had talking about surface frost was from Gladstone et al., and that was looking at the permanently shaded regions in the North and South Pole and comparing that to models of the reflected or the absorption of surface water in this wavelength region here. Here we're off of the absorption, so we called that the off band, and we summed over a range of wavelengths, and then we have the on band here, which we summed over a range of wavelengths as well. And so that off-band to on-band ratio that you'll see referenced when people talk about the LAMP observations is the ratio of the absorption of water. It's giving an indication of how much surface water is present. The other important thing to understand about LAMP is in the wavelength range that we're operating, we can only see the top few microns of the surface. So we can't see any water up depth. We see the water that is on the very surface. We also see the porosity of the surface regolith just at the top few microns. So the results that Randy published were about 0.1 to 2% surface water frost in different permanently shaded regions, and then later Paul Hayne took those observations and compared them with Diviner and found that increase in the ratio at lower temperatures, and then Elizabeth Fisher built on that and compared the Diviner and the Lola observations and some of the LAMP observations to look at the temperature indications for surface frost. We also are able to detect geologically young craters because we're able to see the surface porosity, and this was not expected when we designed the instrument, but we were able to see that the albedo, I think I'm pointing wrong, over here, the albedo is brighter within a permanently shaded region, which generally the PSRs are dark in the Lyman alpha, and that is because the surface porosity is very high, about 70 to 80% compared to the outside region where it's lighter, and that's because the surface porosity is about 40 to 50%. But these two bright regions in Faustini and Slater coincided with the ejecta blankets of two craters that are about 1 kilometer in diameter. And when we compared with the mini RF observations, they indicated increased surface roughness of those ejecta blankets as well. Both of those together suggested that these are geologically young craters. So this is a new discovery that we're able to, a capability that we have with the instrument. So we have delivered to the PDS maps where we're summing over the off band and summing over the on band to get better signal to noise. And we would like to do more with our observations because we take measurements as a function of wavelength at about 2 nanometer bins. So we have been working on a spectral mapper to see if we can get better observations of surface hydration and possibly detect other volatiles that are on the surface of the PSRs. And this is, as Noah was talking yesterday, one of the benefits of a very long-term mission, because we've been in orbit for 10 years, we continue to take observations, and the more orbits that we get with LAMP, the more signal that we have to try and get spectral observations. So what I'm showing here is our spectral mapper for daytime in the off-band wavelengths, and you can see that this is the South Pole here in the middle. And then as you get closer to the equator, the brightness that we measure is significantly higher, orders of magnitude higher than at the poles. So we are photon starved at the poles. This is the spectra for the poles, and you can see as a function of wavelength in the Lyman alpha at night. So this is the night, not the day. And at night, we have a large number of photons that we're able to measure in the Lyman alpha. So our Lyman alpha maps have very good signal to noise, and we have a lot of confidence in those. These other ones, the on-band and the off-band, we have a very low signal that decreases with wavelength. So as you get into the longer wavelengths, we have a smaller signal because this is all coming from starlight. In order to take these brightness measurements and turn it into a spectra of the albedo, which is what we need to understand the surface properties and the volatiles that are present, we have to know the illumination conditions, how many photons are actually coming to the surface. So we have been working on improving that because we need to take into account every source of illumination to the PSRs. The main source of illumination, as I said before, is the Lyman alpha, which is the Lyman alpha sky glow. That's shown here from Randy's paper. And as I said, we get a lot of photons from that. We also have UV bright stars, and when we originally developed our maps, we were looking at the 1,000 brightest stars that IUE has spectra measured for as a function of wavelength so that we can get the most accurate spectra. And these are shown here on the right. Oops. Okay, and the red is the added stars because we realized that there are UV bright stars that the IUE does not have spectra for. So we have 3 graduate students that are working on LAMP. They're all here today if you want to meet them and talk to them. Ben Byron is the one who has been doing this work. So he's taken a cruise model and modeled the spectra of 1,000 more stars and added those to our illumination model so that we can better account for the illumination on the surface of the moon. That increased our estimated photon flux to the surface of the moon by about 15 to 20%. So not a very large amount, but enough that it's important and we need to consider that. There are 2 other sources of light for the permanently shaded regions that we've looked into. One of them is earthshine. What I'm showing here is a study that we did early on in the mission, looking at whether we see earthshine reflected off of the moon. Now this is more of an equatorial region, and earthshine is going to be in the oxygen band of our wavelengths. And you can see here the earthshine is showing up in a very narrow wavelength range that's in the box here. Now what I've done is I've taken a study of this wavelength range and this wavelength range to see if in the South Pole region we see any indication of earthshine, and I see no difference between these wavelengths at all, so we don't see any indication that earthshine is influencing our observations of the permanently shaded regions. One other source of illumination that we do see and we have to consider and that we have to take into account but is very difficult is sunlight. So the wavelengths for sunlight to affect our observations are primarily in the off band. Now, sunlight scattering into the permanently shaded regions is very valuable. ShadowCam is going to be using this sunlight to take pictures of the permanently shaded regions, but for us, it contaminates that off band and that off to on ratio. So the way that we deal with that is we restrict the solar zenith angle from our observations for when we make maps so that we are not allowing sunlight to contaminate our observations. This is something that Randy did in his paper, and it's something that we still continue to do. But it's also an opportunity for us because we can see sunlight reflected into the PSRs, and we can actually look for features, as I'll show in a moment. So this shows some of the products that we're working on for our spectral mapper. On the left, we have the Lyman Alpha map, and as you can see, it's a really well-detailed map where you can see the permanently shaded regions, and this pointer is not working at all. But on the left, you can see the permanently shaded regions are well defined because their albedo is so much darker than the sunlit regions. You could practically map the PSRs using our Lyman Alpha map. On the right, I show the on band where I've summed over I've summed over the observations in the on band, and there's a lot more noise in those observations even after several years in orbit around the moon. So but you can see that the on band is darker for the permanently shaded regions. You can see Haworth, Shoemaker, and Faustini on there. This shows the off band when we do not restrict the solar zenith angle. So if you look at the three large craters, I'll switch back and forth. You can see that there is sunlight scattering into them. Particularly here with Shoemaker, we can see a crater in the interior. The rim of that crater is lighting up. So we can see some of these features inside of the crater. And that's something that I'm looking at is the features that we're able to observe and see if there's any difference in surface properties. But when we're looking for surface frost, this shows when we restrict by 91 degrees. So you can see that the scattered sunlight has been eliminated from the interior, and you can see that the off band is darker as well in those three craters. So, and then this shows the spectrum that we get for the albedo. It is a work in progress. This is not a final product, but it's an example of what we're working on doing, and we can isolate the PSRs and look at their individual spectra this way. We're still working on this, so don't take it as a final product. One of the things that we have another graduate student who's working on, Lizeth Magana, and she's here, is looking at not just surface frost, but seeing if we can find any indications of some of these other volatiles that were observed, particularly in the L-cross plumes. So there's things like ammonia, CO2, SO2 that might be of interest as well and might be visible in the UV. So what we're looking at, what she's going to be doing, is separating out these spectra according to the temperature measured by Divine, or the maximum temperature, and looking at the stability point for these temperature, or the stability temperature for each of these volatiles, and seeing if the spectra looks different. And this is going to require a lot of work on her part and a lot of data, so this is a work in progress as well. So in summary, we are making very good progress at additional products that are going to be made available when we have confidence in our signal to noise and our process of producing these data products. And if you're interested in learning more, please talk to me or any of our students who are helping work on this product. And as a last note, we have a Lunar Polar Volatiles workshop coming up in August, and watch for results from that. And I'll take questions.
Are there questions? Rick?
Kathy, that's really cool, new stuff that's coming out, and I'm really looking forward to having access to it. I'm sure other people are too.
Yes.
I have a kind of a funny question. Are you ever in a situation where you've got Venus light coming in, reflected light coming into it would be, evening local times or morning local times?
In the permanently shaded regions, I'd say no. I don't know if it would be bright enough for us to observe on the surface of the moon. It may not be, because the earthshine, the signal from earthshine is so weak. I think he had to increase it and scale it when we, oops. Yeah, I think the signal would be too weak. The earthshine signal in and of itself is so low, and that's so much closer.
I'm just wondering how abrupt and distinct is the absorption edge in the far UV, because a lot of metal oxides have these same band gaps and they can absorb light in the exact same range. So how do
Yeah.
you discern the absorption of the regolith, if you will, with the water itself?
I am not the best person to answer that. Amanda Hendricks is a better person, and she's in the back of the room. But I believe there can be some variability to the location of that absorption to
Right there.
that.
Yeah, that's right.
Oh, shoot. There can be some variability based on grain size, I believe, and maybe temperature, but I am not an expert on that, so. It's generally in that region, and that's why we have the off-band covering such a wide range and the on-band covering a wide range as well, so that we can account for any shift in that absorption edge.
Is there another question?
Tom, I'll just chime in a little bit. I mean, you're right, it's hard to sometimes pinpoint it exactly, but we do try to use other clues also, like spatial orientation, also temporal variation, if we see it, to help us understand what it might be.
All right, thank you. Very interesting.